Hello everybody. In this series of videos, I will be discussing the concepts of chemical and ionic equilibrium in detail. Now most of the students find this chapter difficult because the mistake that they do is they try to memorize a formula, and when a question comes, they straight away try to put in the numbers in that formula. In this chapter, your approach to solving a problem should be that you understand the concepts, and whenever a question comes in front of you, try to correlate it with the concept. Because if there is a slight change or a slight modification in the application of the formula, you can identify it very clearly if you know the concepts. But merely memorizing a formula wouldn't work in this chapter. Now in this video, I have discussed the concepts in a lot of detail, which will really help you to get a firm grip on this chapter. So if you feel that you're not very clear with chemical and ionic equilibrium, then do stick with me up till the end of this video, in fact the entire video series, and I can assure you that chemical and ionic equilibrium will be much easier for you than what it currently is. Let's get started with the first thing I want to cover in this video, that is the law of mass action. Say for example, I give you a reaction A plus B giving C. Your reactants over here are A and B and the product is C. So the law of mass action states that the rate at which the reaction proceeds, the rate of reaction, is proportional to the concentration of reactants. Now for all those who do not know what is concentration, say for example you are taking a vessel and that vessel is of volume equal to V liters, and let's say of that substance A, the substance A, you are taking n number of moles of the substance A. The concentration will be number of moles of A that you have taken divided by the volume of the vessel, or not volume of the vessel. Let's say you are putting V liters of water in that solution or in that vessel. So V is the volume of water that you have put, or let's say V is the volume of solution. So number of moles of A that you have taken divided by the volume of solution is what we say concentration. That volume of solution is always written in liters. So in liters means most often it is written in liters. That's the most widely used way of writing volume. And whenever you write volume in liters, the unit for concentration will be capital M, that is molar. And molar, like you can see from the formula, it is moles per liter. 1 liter is the same as 1 dm cube. So molar is often stated as moles per dm cube also. So this is concentration, number of moles per unit volume, where the volume preferably is written in liters. And that V is volume of the solution. So law of mass action states that the rate of reaction will be proportional to the concentration of your reactants, and the reactants are A and B. So that will be A multiplied by B. When I say A in square brackets, I mean the concentration of A. So that square bracket A will be a number itself, something like 1, 2, 2.5, 3.5, something. And this means concentration of B. If you want to remove the proportionality sign, you can just write an equal to sign and a constant K here. And that constant K is what we call the rate constant of the reaction. And that R out here is the rate of reaction. Say for example, I change the equation slightly, and instead of A, I write 2A. Then as per law of mass action, rate has to be proportional to the concentration of reactants. The reactants are 2A plus B. Imagine 2A plus B as A plus B. Then the rate will be proportional to A into B into A. But that A into A can be written as A square. So your observation over here is that if the coefficient of A was 2 in the balanced chemical equation, then that too will become the power of concentration of A in the equation that you write for rate of reaction. That's the most important, that's one of the most important things you need to see in the law of mass action. Now instead of 2A plus B giving C or any such random reactions, let's take a general reaction. A general reaction of the type AA plus BB giving CC plus DD. So that's your reaction. And can you write the rate for this reaction? Of course you can. You need to use the same rule that you just learned. As per law of mass action, the rate of reaction will be K into, it will be A power A into B power B, because A and B are the coefficients of your reactants. Now let's go a step further into this. Instead of considering it a one-step reaction or an irreversible reaction, let's consider that the reaction is reversible. So AB will react giving you C and D, but C and D further will react, giving you back A and B. So now this will be termed as rate of forward reaction, and instead of K we will use the subscript F. I mean, instead of K we will write KF, indicating that this is the rate constant of forward reaction. Can you write rate of backward reaction in a similar way? Of course you can. So if you consider the backward reaction, your reactants are C and D. So the rate of backward reaction will be the rate constant Kb, the reactant C power its coefficient which is C, into the reactant D power its coefficient which is D. So that is how you can write rate of backward reaction. Now in a reversible reaction, what will happen? Say for example, I am just simplifying the equation and writing it as A plus B giving C plus D. And initially I have taken 10 moles of A and 10 moles of B, and there were no moles of C and D in the vessel that I have taken. Now A and B will start reacting, and as they start reacting, C and D will get formed. So let's say at some point of time or after a very long time, I see that in the vessel I have 7 moles of A left with me and 7 moles of B left with me. So we can conclude that 3 moles of A and B have reacted to give us 3 moles of C and D. So in the vessel, along with 7 moles of A and B, we will have 3 moles each of C and D also present. Now this concentration or these numbers will remain constant. So when the concentrations of A and B don't change, or the reaction does not proceed in any of the directions, we say that equilibrium has been established. Now at equilibrium, does it mean that everything has stopped? The answer is no. At equilibrium, the reactions are still going on. So say for example that 1 mole of A and B are reacting, giving you 1 mole of C and D. The concentrations will become 6, 6, 4, 4. But at the same very time, 1 mole of C and D will also react, giving you 1 mole of A and B. So again that 6, 6, 4, 4 that had become will now become 7, 7, 3, 3. So 7, 7, 3, 3 will remain, but at that point the things have not frozen. I mean, the things have not become stagnant. The forward reaction is also going on and the backward reaction is also going on. It's just that the speed at which the forward reaction is going on has become equal to the speed at which the backward reaction is going on, and that is why the number of moles of ABCD that I have in the vessel are remaining constant. So at equilibrium we conclude that the rate of forward reaction and rate of backward reaction become equal. So if we try to equate the rate of forward and rate of backward reaction, considering that equilibrium has been achieved, what we will get is Kb, sorry, on the left hand side it will be Kf, A power A, B power B, and on the right hand side you can just write down that Kb over here. So that will be Kb, C power C, D power D. Take that Kb on the left, you will have Kf upon Kb equal to C power C, D power D divided by A power A into B power B, and we call this term K. K is called equilibrium constant for a reaction. Now this is where the concept ends. Now this is where you need to start analyzing the equation that you have just learned. So this equation is the equation for equilibrium constant for a given reaction. How are you writing that equilibrium constant's formula or the expression for equilibrium constant? In the numerator, what you are taking are the products, and they are concentrations. The concentrations of products are being raised to some power. For example, the concentration of C is raised to C, and that C is the stoichiometric coefficient in the balanced equation. So you have C power C, D power D in the numerator. That is for writing the expression for K, which is the equilibrium constant. The numerator will be taken as the concentration of products, and their powers will be the coefficients in the balanced chemical equation, and the denominator will be containing the concentrations of reactants, and their powers will again be the coefficients of the individual reactants. So that is how you are going to write the expression for K, that is the equilibrium constant of your reaction. Now try to apply the entire thing to the example that we had taken. If I tell you to evaluate the equilibrium constant for this reaction, you will write the K value for that reaction as 3 power 1 into 3 power 1 because it should be C power C and D power D, so I need to take the products first. So the concentration of C, which is 3, and the power of 3 will be the stoichiometric coefficient in the equation, which is 1. So 3 power 1 into concentration of D power 1. You might be wondering why I am taking the concentration as 3, because I had mentioned that this 10, 10, 0, 0 or 7, 7, 3, 3 were actually the number of moles. Let us just go ahead with the assumption for now that whatever solution we have taken is a solution of 1 liter. Had it not been 1 liter, had it been 2 liters, I would have said the concentration of C is 3 upon 2, because I said concentration is number of moles per unit volume. But for now, let's take that concentration as 1 and go ahead with the expressions. So that will be 3 upon 1, which is 3, into 3 upon 1, which is 3, divided by the concentrations of A and B, which are 7 upon 1 and 7 upon 1, that is 7 and 7. So the K value for this reaction will be 9 by 49. Now think over it. What if I change the concentration of any one of the species in this reaction? Like for now, I have 7 moles of A and okay, for now equilibrium has been achieved, and at equilibrium I have 7 moles of A, 7 moles of B, 3 moles of C and 3 moles of D. Let us say that in this equilibrium condition, I am adding 5 moles of A extra in the solution. So now instead of 7 moles of A, I get 12 moles of A. Now if I get 12 moles of A, the system will no longer remain at equilibrium. It will no longer remain at equilibrium because now if you try to evaluate the K value, the K value will now become 3 into 3 upon 12 into 7, that is 9 upon 84. The reaction will not allow this to happen because the K value for the reaction is 9 by 49. Now why is the reaction so rigid on the K value? We stated that K was the equilibrium constant. You called it a constant, right? So constant means its value will never change. The reaction will not allow you to change the value of that constant. So now by putting 5 moles of A extra in the solution, you have tried to change the value of K. The reaction will not allow you to do so because the value got decreased and the reaction wants its value to be 9 by 49. The reaction will try to increase this value and make it equal to 9 by 49. If the reaction wants to increase this value, increase the K value, then how will the reaction try to do it? For increasing the K value, keep in mind the expression of K was this. For increasing the K value, it is necessary to increase the numerator, which are the products, or you can decrease the denominator, which are the reactants. That is the way the reaction will try to increase the value of K. If you put it over here, trying to increase C and D means trying to increase this and trying to decrease this. If you are decreasing this and increasing this, it means that the reaction is proceeding in the forward direction. So our conclusion is, because we are putting 5 moles of A extra in the solution, the reaction proceeded in the forward direction. If I tried to increase the concentration of reactants, the reaction tried to increase the concentration of products so that the K value remains unchanged. So that is the entire phenomenon. If you try to increase the concentration of reactants, the reaction will try to increase the concentration of products so that K value remains constant. In a similar way, think over it. What if it was 7733? Okay, before I get to that point, let's just finish off this part fully. So I had 12733, right? I said that the reaction will try to decrease the concentration of AB and increase the concentration of CD till the K value becomes equal to 9 by 49, because currently it's 9 by 84. Say for example, for this condition, I ask you the concentrations at equilibrium, that is the new concentrations of ABCD at equilibrium. So let us say that for getting up to equilibrium, X moles of A have reacted with X moles of B, and that has given you X moles of C and X moles of D. So I will be left with 12 minus X moles of A and 7 minus X moles of B and 3 plus X moles of C and 3 plus X moles of D. Now this will be the concentration of ABCD in my reaction at equilibrium. So at equilibrium conditions, I can say that K will be equal to concentration of C into concentration of D upon concentration of A into concentration of B. But the numbers will now not be 3377. The numbers will now be written as 3 plus X upon 12 minus X into 7 minus X. and I am equating it with K. Keep in mind the K value for this reaction was 9 by 49. Now if you solve this entire equation, it will be a quadratic equation, a little difficult to solve, but it's okay. Okay, it wouldn't be a quadratic equation. Yeah, it wouldn't be a quadratic, no, it will be a quadratic equation. So that quadratic equation will be a little long for you to solve, but it's okay. You will get the x value that you are looking for, and after you get the x value, you can just put it over here. Here and here. So when you put that x value in these numbers, you will get the concentrations at equilibrium, and these concentrations will now be different than 7733 that you initially had. So what I am trying to tell you over here is equilibrium constant K, the K value will never change even if you change the concentrations here. In fact, the reaction will try to manage, or it will try to bring the concentration values in such a way that this expression turns out to be equal to the K value for that given reaction, which is always fixed. Okay, so that's what the calculation part involved in this reaction is. Now say for example, the 7733 part which you had. You had 7733 at equilibrium, and in that 7733, instead of adding 5 moles of A extra, let's add 5 moles of C. So if we add 5 moles of C, this will now become equal to 8. Try to calculate the K value again. The K value will be 8 into 3, which is 24, upon 7 into 7, which is 49. But for this reaction, the K value was 9 by 49. Because the K value is increasing, the reaction will not try to let the K value go up like 24 by 49. If the K value has gone up to 24 by 49, the reaction will try to decrease that K value, and it will try to bring it to 9 by 49. The way it will do it is by increasing AB and decreasing CD. Keep in mind, this time it became 24 by 49, so the reaction was trying to decrease K value. For decreasing K, the numerator must be decreased. So C and D have to be decreased, and the denominator AB must be increased. So A and B has to be increased. That means that the reaction will go in the backward sense now. So it will be C and D reacting to give you A and B, and that reaction will keep continuing till that K value does not become 9 by 49. Let us say X moles of C react and X moles of D react to give you X moles of A and B. So at equilibrium, the concentrations will now be 7 plus X, 7 plus X, 8 plus X, and 3 plus X. And now you can actually say that because these are the concentrations at equilibrium, you will have 9 by 49, which was the K value. K value for this reaction, 9 by 49, will be equal to C power C, which is 8 plus X power C. I mean, power C means the coefficient of C, which is 1 only, into 3 plus X, that is concentration of D power 1, divided by the concentration of A and B. Again, by solving this quadratic equation, you will get the X value. Do not worry for JEE mains and advanced, because in mains and advanced these kind of complicated expressions don't come. I have randomly taken numbers, that is why the calculations are turning out to be this complicated. You need not perform all the calculations, don't worry. Just analyze the way we are solving things. So after you have learned how to write this equation, see how the terms are going to behave in that equation. Like when you were substituting CDAB, I am taking care to see that whatever CDAB I am substituting are actually the concentrations at equilibrium only. They are not any concentrations at some random point of time. Also the K value, that is the equilibrium constant, remains constant for the reaction no matter how much ever the concentrations of ABCD keep changing. So K does not depend upon ABCD. There is only one factor which can affect the K value, that is the temperature. Okay, so I have written it over here. It is only temperature that can change the K value. K value cannot be changed by any other factor other than temperature. So if you change the concentrations, you just saw that K value will remain the same. Okay, so that's something related to calculations. If you haven't understood this, or if you have missed something in whatever I have spoken, rewind the video and check the full calculation part once again. If yes, let's go ahead with the next part. Now with the help of all the calculations that you have done over here, you can easily understand something what is famously called the Le Chatelier's principle. So Le Chatelier's principle tells you that if you try to change the reaction conditions in some particular way, the reaction will respond in the opposite way. So if you try to increase the concentration of reactants, the reaction will try to decrease the concentration of reactants. If you try to decrease the concentration of reactants, the reaction will try to increase the concentration of reactants. If you decrease the concentration of products, reaction will try to increase it. If you increase the concentration of products, reaction will try to decrease it. If you understood, well and good. If not, just get back to the numbers that you had taken over here. So what you had done was you had taken 12 moles of A, right? When you took 12 moles of A, you saw that the reaction was making A and B react and forming C and D. So that means that if you try to increase the concentration of reactant, the reaction tried to decrease the reactants and tried to increase the products. That is, you increase the reactants and reaction tried to decrease the reactants. That is what Le Chatelier's principle is. You try to increase one thing, reaction will try to decrease it. You try to decrease one thing, reaction will try to increase it. In the second example also, you tried to increase C. That is, you had taken 8 moles of C, you had 3, 3 and 7, 7 at equilibrium, right? So you were putting 5 moles of C extra. You are taking extra C. So you are trying to increase the concentration of products. What did the reaction do? The reaction tried to decrease this and increase this. So because you tried to increase the concentration of products, the reaction tried to decrease it. You can take some numbers and try to verify the other cases also. That is, what if you try to decrease the concentration of reactants? Say for example, this was 7733, right? 7733. You try to decrease the concentration of reactants. As per Le Chatelier's principle law, what did we say? We said that if you try to decrease the concentration of reactants, the reaction will try to increase it. It will behave in the opposite way. So let's try to decrease A. A was 7 moles. Let's assume I am taking out 5 moles of A. So I am now having 2 moles of A, 7 moles of B, 3 moles of C and D. What's the K value? The K value will turn out to be 9 by 14. But you know very clearly that for this reaction the K value was 9 by 49, and until and unless you change the temperature, K value will not change, and we are not changing the temperature. So the K value for this reaction will remain 9 by 49, and because the value has increased by removing A, when you removed A, the value became 9 by 14. The reaction will not let it remain at 9 by 14. The reaction will keep making the species keep reacting with each other till the K value reaches 9 by 49. So from 9 by 14, if you want 9 by 49, you have to decrease the K value. And for decreasing the K value, you have to increase AB, and you have to decrease CD. So for decreasing CD and increasing AB, the reaction has to go in the backward sense. So what did you conclude? That you tried to remove the reactants. Because you were removing the reactants, the reaction tried to increase the reactants and decrease the products. That is the same thing which I stated, that is Le Chatelier's principle. You try to decrease the concentration of reactants, reaction will try to increase it. You try to decrease the concentration of products, the reaction will try to increase the concentration of products. So if you remove, say for example, this was 7733, right? Let's say for example you remove the 3 moles of D that have formed. So if you remove the 3 moles of D that have formed, that is, you are decreasing products, the reaction will try to increase them. So this will keep decreasing and this will keep increasing because you removed the 3 moles of D that were getting formed. So that is your Le Chatelier's principle, only first point. That is about concentration of reactants. So for concentration of reactants, like I said, if you try to, the thing which I said, you try to increase one thing, the reaction will try to decrease it. You try to decrease one thing, the reaction will try to increase it. The second point in Le Chatelier's principle is about temperature. The principle remains the same. Say for example, one of the reactions is exothermic and the other is endothermic. Consider the same reaction and let's consider that some heat is also liberated. So if you realize the forward reaction is releasing heat, it is exothermic in nature. The backward reaction goes with the absorption of heat. So C plus D plus heat is giving you A plus B. So the backward reaction is endothermic. Now think over it. If you try to increase the temperature, don't think in terms of K now, just think in terms of Le Chatelier's principle. You try to increase the temperature, reaction will try to decrease the temperature. How does the temperature get decreased? It gets decreased if heat is absorbed. So if you try to increase the temperature, reaction tries to decrease the temperature by absorbing heat. So the endothermic reaction will be favored. So the endothermic reaction is favored if the temperature increases. And what if you try to decrease the temperature? If you try to decrease the temperature, the reaction will try to increase temperature. It will try to increase temperature by forming heat or by generating heat, and heat is generated in the forward reaction. So the exothermic reaction will be favored if the temperature decreases. Now remembering this was a little difficult for me, so I tried to correlate it with the concentration part only. So I took heat as concentration only. So let's say if I am increasing temperature, if you increase temperature, you are increasing this, and if you try to increase this, reaction will try to decrease this and increase this. So if you try to increase heat, the reaction will proceed in this direction, and if you try to decrease it, that is if you try to cool down the entire solution or the reaction, if you try to cool down the solution, that is you remove heat, the reaction will proceed in the forward sense. So you can correlate that thing with the concentration part as well and understand that which way the reaction will proceed. If that is comfortable, then fine. If not, then the concept which I spoke of is the one which is written in the textbooks. That is, you try to increase temperature, the reaction will try to absorb heat, and the endothermic reaction will be favored. And similarly for the exothermic reaction part. So that is the Le Chatelier's principle in terms of temperature, and the third one is in terms of pressure. Now for pressure, you need to get back to the way you are writing the equilibrium constant. When you were writing equilibrium constant for this reaction, the terms here were actually the concentrations of the species in the solution. But this is done only if the species are in the solution form. But what if these A, B, C, D were not something in solution but they were gases? So if any one of them turns out to be a gas, or let's say the entire reaction is carried out in the gas phase, then we don't say K is the equilibrium constant, or we say it's the equilibrium constant only, but we write it as Kp. So in that case, if I want to write Kp, in that case means in the case where everything is in the gaseous form, your reaction is carried out in the gaseous state. In that case, Kp will be written as the pressures of the gases. Instead of concentration, you will have pressures. So this Kp will be, instead of concentration C power C, it will be pressure of C power C multiplied by pressure of D power D divided by pressure of A power A into pressure of B power B. There is a conversion of Kp and Kc, or I can say I can establish a relation between Kp and Kc. It can be done very easily by using the ideal gas equation. For any gas, we know that PV will be nRT. Take that V on the right hand side. So P will be nRT upon V, and that N upon V can be written as concentration C. So I have P equal to CRT. So I can write PC as concentration of C into RT. So we have concentration of C into RT as PC, and the whole power is C. So I will have C power C into RT power C. Then I will have D power D, RT power D, A power A, RT power A, and B power B, RT power B. So if I combine all the terms, they would look something like this. The power of RT is going to be C plus D minus A minus B. So C plus D minus A minus B, I can say that is the number of moles of products minus the number of moles of reactants. So in the power of RT, we have C plus D minus A minus B. We call it delta N. So we simply say RT power delta N. And that delta N is C plus D minus A minus B. Whenever you are writing that delta N, you need to take care to see that C plus D minus A minus B, the number of moles that you are adding and subtracting, have to only and only be considered for gaseous species. So for example, if D was a liquid species, I wouldn't have considered the term D here. I would have simply said C minus A minus B. So consider only those terms in delta n which are in gases. If something is not in the gaseous form, in writing RT power delta n, you should not consider the value or the coefficient of that particular term. If I continue with this equation, then Kp becomes, this term was Kc into RT power delta n. That's an equation you need to remember. There are questions in JEE mains that come from this equation, that come based on this equation. So I have Kp is Kc, RT power delta n. For example, I give you an equation of the type H2 plus I2 in equilibrium with 2Hi, and let's say that all of them are gases. Then what will be the delta n value for this reaction? Delta n will be the ones that you have in product, which is 2, minus the number of moles which you have in reactants, that are 1 and 1. So 2 minus 1 will be 0. So delta n will be 0 and RT power 0 will be 1. So for this reaction, Kp will be equal to Kc. That delta n may not always be 1, it can be positive, negative, anything, but depending upon the delta n value, this relation will be followed between Kp and Kc. Now since we have discussed this point, that if anything is in the gaseous state, then instead of concentration you write its pressure. Then let's discuss one point over here also for K, that whenever you are writing terms over here, that is C, D, A, B, these are the concentrations of species that are there in the solution. For example, you take something like a stone and put it in water. That stone is not soluble in water, so that stone will not appear in the equations over here. It will be like there is a stone here, some X moles of a stone plus something. That X moles of a stone, this stone is solid in nature, whereas A and B are aqueous in nature. I am calling A and B as aqueous because they have dissolved in the solution, but that stone is not dissolving in the solution. So that stone, even if it is a part of the reaction, you will not write it in the equation over here. This K is written only for those species, or while writing K, you will write only those species which are dissolved in the solution, that is, which are the ones in the aqueous phase. The solid things, the solid parts of the reaction are not going to appear in the expression for K. So these are some things about Kc, Kp and all that you need to know before you go ahead with the third point of Le Chatelier's principle, which is about pressure. Now when it comes to pressure, say for example, you are carrying out reaction in a vessel and you are decreasing the volume, or decreasing the volume means you are increasing the pressure. Decreasing volume or increasing pressure would mean one and the same thing. So pressure increasing or decreasing volume are one and the same thing. So if you try to increase the pressure by decreasing the volume, then what happens is in your mixture, the number of moles per unit volume have increased. It's like number of moles are the same, but because you decrease the volume, number of moles per unit volume are decreasing when you increase the pressure or decrease the volume. So number of moles per unit volume are going to increase. So the reaction will try to decrease the number of moles. And for decreasing the number of moles, you need to check the balanced chemical equation. Say for example, it's the reaction between nitrogen and hydrogen giving you ammonia. In this reaction, on the left hand side, the number of moles that you have are 5. There are 5 moles on the left, and on the right hand side you have 2 moles. All of them are gases, okay? So you need to consider the moles of gases only when you are studying this concept. So there are 5 moles here and 2 moles here. Now like I said, if you try to decrease the volume or increase the pressure, the number of moles per unit volume increased, the reaction will try to decrease the number of moles. In which direction are the number of moles decreasing? The number of moles are decreasing here. Sorry, it wouldn't be 2N2, it would only be N2, so this will be 4. The number of moles are decreasing in the forward direction, and that is why the forward reaction will be favored in this example. If you try to increase the pressure, what if you try to decrease the pressure? Now decrease the pressure or increase the volume will mean one and the same thing. So this was your vessel, increase the volume. If you increase the volume, the pressure automatically drops down. So if you drop down the pressure or you increase the volume, then number of moles per unit volume are going to decrease, because the number of moles would remain the same, but because of volume increasing, number of moles per unit volume went down. So now the reaction will try to behave in the opposite manner. That is, it will try to increase the number of moles. And because it is trying to increase the number of moles, the reaction will proceed in the backward direction because number of moles are increasing in the backward sense. So this reaction will be favored in the backward direction if you try to decrease the pressure or increase the volume. So that is about pressure. So pressure increases or volume decreases, the number of moles per unit volume will go up, and the reaction proceeds in that direction where the number of moles are going to decrease. Now the application will be different for every equation, but the principle remains this. So this is where I am done with discussing the Le Chatelier's principle, and I am also done with covering whatever content I wanted to cover in this video. Just one last thing, the delta N value, I had written the reaction for ammonia formation, right? N2 plus 3H2 in equilibrium with 2NH3. So the delta N value for this reaction will be 2 minus 1 minus 3, that is minus 2. So Kp will be Kc into RT power minus 2. Okay, just one thing, the application of this result to an equation like this. Okay, so this is where I am done with covering whatever I wanted to cover in this video. Of course, more things are going to come up in the videos which are there, which in the later videos which I am going to make in this series. I hope whatever I have taught in this video has been understandable and somewhere someplace helpful to you in your preparations. Do check out the other videos of this playlist if you have liked it, guys. Thank you for watching.